So let's say start after a couple of minutes. Hope my screen is visible and I am loud and clear. Okay. So my name is Shudran Sadhavan. I am a PhD student at IIT Bombay. I am your facilitator for the uh, live weekly interactive session of NPTEL course code AR18. The course title is Urban Utilities Planning, Water Supply, Sanitation and Drainage. The course instructor is Dr. Debapratim Pandit, who is a professor of IIT Kharagpur at the Department of Architecture and Regional Planning. And I welcome you to the week 8 session. Today is September 15th, and more than 50% sessions are covered. Let's hope you only are joining, you only have joined. For the sake of recording, I am also telling that let's hope the other persons are also able to access the recordings and uh, presentation files, whichever is required for them, whichever they want, they may access that and they can go through if they have not attend the same. And if there are any doubts, they can raise in the discussion forum or they can ask in the interactive session itself. Okay, so we can start today's session. So today's first question is, a wastewater stream is mixed with a river nearby. After mixing, formation of certain zones occurs. Which one of the following zones is characterized by the highest level of treatment of pollutants? Actually, this problem we finished in a hurried manner in the last class. So today's session actually I promised that I would discuss the background of this problem a little bit. So that's why today's class I am starting with this problem. Just to recap. So just to have a recap. So the options are: option A is zone of degradation, option B zone of recovery, option C zone of clear water, and option D is zone of active decomposition. So it was an MCQ, multiple choice question, and the hint was something like this. So I showed a graph which divides the length of the river into five different types of zones: zone A, zone B, zone C, zone D, and zone E. These zones are respectively called as the clear water zones, zone of degradation, zone of active decomposition, zone of recovery, and zone of clear water. All these five zones are together called as the zone of pollution. And the level that we basically see that the level is decreasing, increasing. So this is nothing but the dissolved oxygen level of dissolved oxygen. So the average level of dissolved oxygen is 40%. Let's say the clear water zone and the zone of clear, yes, so zone A and zone E, both the zones are the zone of clear water. All the two zones will have dissolved oxygen percentage of around 60 or 70, and at the zone of active decomposition or zone C, it will decrease to uh, around 15 or 20%. Now we will understand this in a bit deeper manner with a more detailed graph. So let's say the distance downstream is plotted along the x-axis, and these three components, that is species, population, and dissolved oxygen or DO, these three concentration components are plotted along the y-axis. So these are the different composition that is present inside the river water. Okay. Now, as we go in the downstream direction, let's say at x equals to 0, the pollutant material or pollutant effluent stream is introduced into the river water from the municipality drainage system, or let's say any chemical plant. Here the pollutant effluent stream is introduced. Now, as we go along the direction of the river in the downstream, then what happens? These five zones actually occurs as I told earlier. Now, these were based on the DO as we started. Now, here also species and population concentration are provided. So, what are these things? So, these species and these populations are basically the uh, species and population of the bacteria or the virus or the microbes. Those are present in the water who participate in the aerobic degradation of the pollutants that we just introduced in the river water. So what happens? We have seen that the dissolved oxygen, what happens to the dissolved oxygen? It basically decreases and again it increases as per the three zones: 1, 2, 3, 4. So zone 3 is the zone C or zone of active decomposition. Zone 1 and zone 5 are the clear water zones, and zone 2 and 3, 4, there we can see a active decline and active increase of the concentration of the dissolved oxygen. Along with the dissolved oxygen, we can see that the number of species is also decreasing. Number of species of what? Number of species of aerobic microbes, those are present in the river water. So so what happens? Because of the competition between them for the food, they are and also the decrease of the dissolved oxygen, their species also gets decreased. But among all the species, there is a specific type of species which is responsible for treating the specific type of pollutants that is present inside the water. So their number will increase, selectively increase, as compared to the other species, those are present inside the chunk of the microbes of the river water. So, but that specific type of species will selectively increase, and again after the treatment of the water is done and dissolved oxygen normalizes, then these species, this population of the specific type of species will normalize. That will come to its initial position. This is what happens. So I hope it is clear, because there are different types of pollutants that is present inside the water, and all the microbes those are present inside the river stream, those are not responsible for treating every type of pollutant. So some microbes are responsible for treating some specific type of pollutants, so their population will increase at the zone B, C, and D, this region. Okay, and the other species concentration will decrease. for defined other type of pollutants, some defined other type of species population will increase, uh, and so on and so forth. So hopefully this graph was clear. So now we'll move on to our next question. So we'll assume that this graph is clear. Those of you who will be watching the recording at a later stage, if the thing is not clear to you, you can raise the question in the discussion forum, or you can ask a question in the week 9th interactive session. Okay. Now, based on that, based on the understanding, we will proceed to our next question. So the question is as follows. The measurement of biodegradable organic content is usually carried out in the terms of DO, BOD, COD, and TOC. This is an MCQ, so one option will be correct. DO means dissolved oxygen, BO means biodegradable oxygen demand or biological oxygen demand, COD means chemical oxygen demand, and TOC means total organic carbon or total organic content. So based on that, you have to answer. So POD Babu, you didn't answer any question in the last class. Today I'll expect you to answer. Thank you for joining, but you should answer. Otherwise, I would not understand whether you are listening or not. I mean, at least if you are joining, you should listen, because otherwise it will waste double of your time. Later, if you again watch, and then it will just waste your time. So that's why, as you are joining live, so it is expected that you should ask question in live session only, and get your doubts clarified in this session itself. You should not go through this again at a later stage. So yeah, I'll expect you to answer this question. Okay, I'll proceed with the answer. So the correct answer is BOD, biological oxygen demand, or biodegradable oxygen demand. So now uh, we'll see how the biodegradable organic content is usually carried out in terms of BOD, because this is a very important water parameter from the sanitation and treatment point of view. So let's proceed. First, we will understand the concept of BOD, which is sometimes also called as biochemical oxygen demand. So if we see that with time, BOD increases like this S curve, and the second phase of increase is called as the nitrogenous stage, and the initial phase is called increase phase is called as the carbonaceous stage. And between these two stage, there is a one stationary sigmoid structure of the curve. And if we again study that is BOD total, BOD or which is sometimes termed as the LT with time, and L0 is the initial BOD, then we will find out a curve something like this. L0 equals to 1 minus e to the power minus kt, which is the rest of portion, and the bottom portion of bottom area is defined as LT equals to L0 into e to the power minus kt. If we put e to the t equals to infinity, then we will see that e to the minus kt becomes 0. So at infinite, the BOD becomes almost 0, because the bacteria or virus which is present, or microbes that is present inside the water, they almost eat up the pollutants which is contributing towards the BOD, right? And in this case, if we just put here 0, then BODT becomes L0 at t equals to sorry, the upper portion of the curve is t equals to 0. At the t equals to 0, it becomes L0. So as the time progresses, t runs from 0 to infinity, the BOD decreases with time. Okay. So how they decrease the BOD, how the microbes decrease the BOD, that is the BOD of the water. BOD is nothing but the indirect measurement of the pollutants that is present inside the water, that is of the biodegradable pollutants, those are present inside the water. So they are aerobic bacteria or aerobic microbes. They use the dissolved oxygen that is there inside the water. That is not the molecular oxygen of the water. H2O, that oxygen is not they are taking. They are taking only the dissolved oxygen, which has been dissolved in the water with the help of the waves basically. So because of the turbulence at the surface of the water, the oxygen gets dissolved inside the water, and that oxygen is taken up by the aerobic microbes to decrease the BOD. Okay. So now if we have understood this concept, based on this concept we will solve one problem for the better understanding of the concept of BOD. The problem is as follows. An industrial outfall is releasing 4.32 megaliters per day or million liters per day MLD effluent to a river having flooded as 12 meter cube per second. Now this is provided as the volumetric flow rate. Okay. The background BOD level of the river is 0 and BOD in the wastewater is 12,050 milligram per liter. The permissible BOD limit in the river water is 10 milligram per liter. Now, the problem is, so there are several problems. Number one is assuming instantaneous mixing at the discharge point, the BOD of the river water at the discharge point would be in milligram per liter. So we can see that the wastewater stream that is coming out, that is the industrial outfall, has a volumetric flow rate of 4.32 mld. So its BOD is 12,050 milligram per liter, and the river water BOD is 0, which is 12 meter cube per second. Now permissible BOD limit is given as 10 milligram per liter. You have to calculate the BOD of the river water at the discharge point. So after the mixing, assuming instantaneous mixing, what is the BOD post mixing that you have to calculate in milligram per liter? So this BOD limit of the river water, which is given as 10 milligram per liter, will not be utilized for solving the first problem. It is just a mass balance. So 4.32 mld that you have to convert into meter cube per second or meter cube per second, that one you can convert into mld, whichever you like. M means 10 to the power 6. I have already discussed earlier. So 12 into this 0 plus 4.32 into 12,050 milligram per liter. This is the total BOD whole divided by the total volumetric flow rate, that is 4.32 plus 12 in similar units that you have to do. This is the, so A plus B equals to C, and A into CA plus B into CB equals to C into CB, C into CC. That is the basically mass balance equation or concentration balance equation you have to use here. Simple. So I'll wait for 5 minutes. Please calculate it and tell me the answer. Are you trying? Okay, so I'll proceed with the solution. So data given is effluent flow, which is 4.32 mld, which is nothing but 4,320 meter cube divided by 24 into 3600 second. So as it is mld, mld means how much? Million liters means 10 to the power 6 liters. Now 10 to the power 6 liters means 10 to the power 3 meter cube. So that's why you have multiplied 4.32 into 10 to the power 3, which gives us 4320 meter cube. Now ml is converted into meter cube. This is not small ml. Okay, small ml means milliliter. So it is capital ml. That means million liters. Now per day, these things means one day means 24 hours and 3600 second per hour. So day is converted into second. In this way, 4.32 mld is converted into 0.05 meter cube per second. Hope this is clear. So now next effluent BOD is given as 12,050 milligram per liter. River flow is given as 12 meter cube per second. River water background has 0 BOD. So BOD at the discharge point can be calculated by this following formula. So river water flow into river water BOD, that means 12 into 0. This one. Now effluent flow rate into effluent BOD, that means 0.05 into 12,050, that means 0.1. This one. So effluent flow rate into effluent BOD plus river water flow rate into river water BOD. This many milligram per liter into meter cube per second divided by total meter cube per second flow rate. So that means 12 plus 0.05, which is nothing but 12.05 meter cube per second. So with the 12.05 meter cube per second, you have to divide the entire BOD that is present inside the water. After simplification, it will give you 50 milligram per liter, which is the BOD at the discharge point after instantaneous mixing. So if your answer is within 45 and 55, it will be treated as the correct answer. So now we will see the second problem. So the percentage BOD removal required for the industrial wastewater to ensure the BOD in the river water sustains within the permissible limits even at the discharge point in percentage. So the number 2 problem will require this data. The permissible BOD limit in the river water is 10 milligram per liter. So this data will be utilized in the second problem. Okay. The first problem we have calculated already. After instantaneous mixing, there is no treatment. It will give you the total total BOD divided by total flow rate. That will be give you the BOD in milligram per liter after instantaneous mixing at the discharge point. But if we see that it was 50 milligram per liter, but the river water allowed BOD is 12 milligram per liter. So some amount of and entire this BOD is contributed by this effluent. So to maintain it at 10 milligram per liter instead of 50 milligram per liter, you have to do certain treatment. before releasing, right? So that the effluent BOD of 4.3 ml flow rate is not 12,050 before releasing. So it should be decreased to a certain other level, so that after mixing it becomes 10 milligram per liter. That is the idea here. So what amount you have to treat, that percentage you have to calculate. Okay. So again I'll wait for 5 minutes. Please solve this problem. So this is the entire thing we have done up to this point. So we'll solve afterwards. So hope you have understood till now. If you have any doubt, you can ask. The second, first problem's answer is 50 milligram per liter. Now we'll solve the second problem. Please go ahead. Yes, go ahead. What do you want to ask? So we'll proceed with the solution. If you want to ask something, you can ask. Okay. So we'll proceed afterwards. Maximum BOD in effluent to restrict the BOD at the discharge point, that is given in the question as 10 milligram per liter. We'll use this data to calculate this second answer. So 10 milligram per liter means how much? 10 milligram per liter means 10 milligram per liter into 12.05 meter cube per second divided by 0.05 meter cube per second equals to 2410 milligram per liter. Why we did this exercise? So we have to understand that this 10 milligram per liter, this is the BOD after the mixing. So after the mixing, what is the volumetric flow rate? 12 plus 0.05, which is nothing but 12.05 meter cube per second, right? So uh, if we just multiply the concentration with the volumetric flow rate, it will give us the total BOD that is present inside the water after mixing. That should be present inside the water after the mixing. Now, this entire BOD is contributed by this single flow 0.05 meter cube per second, which is nothing but the flow rate of the industrial effluent. So, this 10 milligram per liter, we just translated it in terms of volumetric flow rate of the industrial effluent. So, because the entire contribution is from the industrial effluent only, not from the river water flow rate, which has background BOD of 0. So after mixing, this 10 milligram per liter BOD is coming from the industrial effluent only. After that mixing, again these 5 zones will form. So that, I mean, the microbes that is present inside the water will, with the help of the dissolved oxygen, they will be able to degrade the BOD into the 0 level again. Okay, so that 5 zones formation graphs that we just shown in the earlier MCQ, this is the aftermath, right? So this is the before math. So because if it exceeds the 10 milligram per liter, they will not be able to treat the entire. So the graph that we have seen earlier, that graph will not form. The formation of the 5 zones will not occur. So that's why, for that to happen, we have to first bring down the effluent industrial flow, that is the 0.5 meter cube per second and 12,050 milligram per liter. So we have to bring down this BOD in this flow rate to certain levels, so that after mixing it becomes 10 milligram per liter. So we just translated it. So if we have to maintain 10 milligram per liter after mixing, what should be the BOD at the your industrial effluent before it gets discharged into the river water, that we have just calculated. So within that 0.05 meter cube per second, that BOD must be brought down from 12,050 milligram per liter to 2,410 milligram per liter in order to maintain 10 milligram per liter BOD at the river water after discharge. Okay, so hopefully I am able to make you understand this. Now, percentage treatment required will be how much? You have to bring down from 12,050 milligram per liter to 2,410 milligram per liter. So the treatment amount will be the amount with which it has been decreased. So it will be 12,050 milligram per liter minus 2,410 milligram per liter divided by the 12,050 milligram per liter. So this is the decrease amount divided by the total amount which was initially present inside the industrial effluent, which is nothing but, after simplification, it will give you 80% or 0.8. Okay. So hopefully I am able to make you understand this problem. Just once again go through the exercise what we have done there. I'll wait for 1 minute and tell me if you have any doubt and you are able to understand, I hope. Okay, so with this idea, we will move on to our next problem. Okay. So so if your answer is within 75 and 85, it will be treated as a correct answer. Now, our next MCQ or multiple choice question is, what is a partially separate water carriage system? Option A, systems, those carry both the sanitary sewage and storm water. Option B, systems where domestic and or industrial sewage is carried in one set of sewers and stormwater and salage surface water inside another set of networks. Option C, systems where portion of stormwater is allowed to enter the sewer carrying sewage and the remaining amount flows in a separate set of sewers. D is none of the above. I'll wait for 1 minute to type the correct answer in the chat box. I think you will not type. Still, I'll wait for 1 minute. What is partially separated water carriage system? So there are four systems, three systems description has been provided here, right? So option C is the correct answer. Systems where a portion of storm water is allowed to enter the sewer carrying sewage and the remaining amount of the storm water flows in a separate set of sewers. So this is called as the partially separate water carriage system. Now we'll move on to our next MCQ. Which one of the following units is not a component under the DWATS? The full form is decentralized wastewater treatment system. Option A is pre-treatment settlers. Option B is ABTRs or anaerobic baffle tank reactors. Option C is polishing ponds and option D is leaching pits. Which one of them is not a component under the DWATS? Which one of them is not a DWATS component? That we have to tell. Yeah. So please type the correct option in the chat box. Okay, I'll move on to the solution. So option D, leaching pits is the answer. Okay, leaching pit is is the unit which is not a component under the DWATS. All the other units like pre-treatment settlers, ABTRs, polishing ponds, all of the three are components of the decentralized water treatment system. Now we'll move on to our next MCQ. So in which sewer system the slope of the ground is of little concern? Or option A is pressurized sewer system. Option B, vacuum sewer system. Option D, partially separate system. And option D, combined system. In which of them the slope of the ground has a very little concern? Okay, so we'll move on toward the solution. So pressurized sewer system is the correct answer, where the slope of the ground is little constant. So all of the other sewer systems like vacuum sewer system, partially separate system, combined system, all of the three, in all of the three cases, the ground slope of the ground is taken into consideration. Now, next there is a problem. From a clear water reservoir 10-meter deep and maximum water level at 60 meters, water is to be pumped to an elevated reservoir at 100 meters at a constant rate of 6 LLPH, that is 6 lakhs liters per hour. Based on this data, you have to calculate the bhp, which is nothing but the brake horsepower of the pump. Okay, so these assumptions you have to take. Number one is economic diameter of the rising main you have to consider. Number two, efficiency of the pump, basically the power transfer, is 90% and small f is given as 0.01. And number three, distance is given in 500 meters. Can you do that? Welcome, Deepti. So we are solving a problem now. I will restate the problem for you. From a clear water reservoir 10-meter deep and maximum water level at 60 meters, water is to be pumped to an elevated reservoir at 100 meters at a constant rate of 6 LLPH, that is 6 lakhs liters per hour. Based on the data, you have to calculate the bhp, that is brake horsepower of the pump. Assumptions are: consider economic diameter of the rising main. There is a formula of economic diameter actually that you have to consider. Number two is efficiency of the pump or the power transfer is given as 90%, that is 0.9, and f, small f, is nothing but called as Fanning's friction factor in fluid mechanics. It is given as 0.01 and distance is given as 500 meters, which is nothing but the capital L. Okay, so based on this data, you have to calculate the brake horsepower. Please take copies and pens with you, both of you, and you just try to calculate this problem. I'll wait for a couple of minutes. Okay, I'll give you some hints. So if we see the brake horsepower, or 1 bhp means 746 watt, 745.7, which you can approximately take it as 746 watts. What is a SI unit of power? So first of all, you have to calculate the power in SI unit, that is watts. Then you can convert divide it with 746 to get the value in bhp, which you have to calculate here. Okay, watts means kg, meter square per second cube. Yeah, kg meter square per second cube. Ml square by t cube is the dimension of power that you can keep in mind for ease of calculation. Now the friction factor small f that is given here is 0.01, which is known as Fanning's friction factor. Darcy's friction factor is can be denoted as F suffix D. What is the relation between this Darcy's friction factor and Fanning's friction factor? So the Darcy's friction factor is FD equals to 4 into small f. That means the Darcy's friction factor is 4 times of the Fanning's friction factor. So if you are using the Darcy-Weisbach equation for the calculation of the uh, of the pressure drop, then in the Darcy-Weisbach equation, FD is used. So you can put 4F in the place of FD, because the small f value or Fanning's friction factor value only is given in the question as 0.01. So FD will be 0.04. Okay, so this is one hint. And another one hint is, first you have to calculate in the power in terms of watts. Then you can convert it into bhp or brake horsepower using this conversion factor. So yeah, please go ahead. This is a very good problem. Are you calculating? Do you know how to calculate, or should I discuss the solution? Wait for 1 more minute, then I will proceed with the solution. So if you have partial, if you have also calculated it partially, not in terms of BHP, but in terms of something else, or if you have just calculated the pressure drop only, then also you can state it in the chat box. That this is the answer you have to you have calculated in this way. Okay, I'll wait for 2 minutes because this is not a very simple problem. You can just put if you have gone, let's say, 5 steps, then you can state the value which you have got after five steps and tell me that this is the unit of the step. Yeah. Are you able to do? Tell me, otherwise I'll just solve. Okay, I think let's wait for a few more seconds, then I'll start solving. Okay, so let's start solving. So you see, what are the data given? That is the first thing you have to see. So the discharge Q is given as 6 LLPH, which is nothing but 6 lakhs liters per hour. Now 6 lakhs is given. If you divide it with 1000, it will give you meter cube. Okay. So 6 lakhs divided by 1000 is nothing but 600, right? Yeah. So 600 divided by 600 meter cubes per hour divided by 600 by 360 this many seconds. So it gives you the meter cube per second. 0.167 meter cube per second. Now economic diameter range of the rising main is given by using Lee's formula, which is nothing but range of D is 0.97 to 1.22 into root over of Q, this Q. So Q is given, we have calculated as meter cube per second, and this is the range of the coefficient between which it will vary 0.97 to 1.22. Now if we multiply it 0.97 into root over of 0.167, it will give you 0.396, and if we multiply 1.22 into root over 0.167, it will give you 0.4981 meters. So the range of the economic diameter will vary from zero point 0.4 to 0.5 meters. Okay, hopefully it is clear. Now head in meters it was stated in the question that the reservoir was 10-meter deep and maximum height was 60 meters. So from below 10 meter minus 10, you had to supply the water into plus 60. So plus 60 minus of minus 10 become plus 10. That gives you 70 meters. This is the lift that you have to provide to the water. Now head loss inside the pipe, which are also denoted as HF in meters, is given by the Darcy-Weisbach equation. It is FD into L into V square divided by 2G into D. Now in the question, FD is not given. F is given. So FD equals to 4F that we have just put here. So FD equals to 4F into L into V square divided by 2G into D. Now this V square, we can write it as Q divided by pi D square by 4, because this D is capital D here, economic diameter. If diameter of the pipe is D, then pi D square by 4 is the cross-sectional area of that pipe. If volumetric flow rate Q is 0.167 meter cube per second through the pipe, and if you divide it with the cross-sectional area, that is pi D square by 4 of the pipe, then we get the velocity, because cross-sectional area into velocity gives you the volumetric flow rate. So volumetric flow rate divided by cross-sectional area, that means Q divided by pi D square by 4 gives you the V. So that 4 from denominator it came to the numerator, it became 4Q divided by pi D square. This is nothing but the V and air whole square. Okay. Now upon simplification, this F is given in the question as 0.01. So 4 into 0.01. L is given as the distance 500 meters into 4 into Q, we just have calculated 0.167 meter cube per second, divided by pi that we have written this whole square. Okay. Now this d square means d to the power 4. D to the power 4 came into the denominator and it becomes d to the power 4 plus 1 d to the power 5. 2 into g, this is the gravitational acceleration. These all the values are kept same except the d to the power 5, because it has got a range, right? So upon simplification of the entire thing, it gave you 0.0461 divided by d to the power 5 meters. Now if we just put the range of the d, it will give you 4.7327 when d is 0.4 meters and 1.5 meters when d is 0.5 meters. Okay, now you just put the d values in this form, you will get this range 1.5 to 4.7. So the range of the total head, which is nothing but HT, denoted as HT meter, HT becomes, so 1.5 to 4.7 plus this H, which we have calculated earlier. So it becomes 70 plus 1.5 equals to 71.5, and this 70 plus this 4.7 gives you 74.7 or approximately 75 meters. So if you have calculated up to this portion, then 50%, more than 50% of the problem you have understood. Okay. If you have not calculated and able to understand, then okay. If you have not calculated and not able to understand, then please ask whether up to this point it is okay or not. Now the real solution comes into the picture. This is the total head drop, that is the pressure drop of the liquid water that we are just getting here. This head you have to provide in the pump with an efficiency of 0.9. So the power that we will be supplying in the pump, that into 0.9 gives you this head. So that power, if you want to calculate, you have to divide it with 0.9. So this range 71.5 to 74.7, that you are dividing it with 0.9. That gives you the head, actual head, considering the 10% loss. Okay. Now, why the other terms are coming into the picture? Because from head meter, you are calculating it into watts or power unit. So if you are having the pressure drop head in meters, you can calculate the power in watts using this formula. Power P equals to Q into rho into H into G. Okay. So this H is there, Q into rho. These are these two terminologies. Q means this volumetric flow rate, Q into H into rho. H you have calculated, rho means the density of the water, which is nothing but 1000 kg per meter cube, or 1000 gram, or 1 gram per cc. 1 gram per cc means 1000 kg per meter cube in SI unit, because all of the units are in SI unit. So that's why we have calculated Q, H and rho in SI units. Okay, divided by 0.9. This is the efficiency. So these four terminologies I hope you have understood. Now that gives you the watt. What happens in this case? Here you have to calculate the watt into, you have to convert that calculated watt into brake horsepower. So that I have earlier stated in the hint, one brake horsepower gives you 746 watt. So 746 or 75 comes in the denominator, 750. So if you divide that thing with the G that is present at the numerator, G means 9.81. So 746 divided by 9.81 gives you something like 76. And upon simplification, the entire term gives you this thing, 177.61 to 185.455, because of this range, 71.5 to 75. This range will come approximately. So if you have got your answer around 180 plus minus 10, let's say 170 to 190, if you have got, it will be considered as the correct answer. Okay, so none of you have calculated, so hopefully you are able to understand the last line also. If you are not able to understand, then please tell me, I will again discuss. Otherwise we will take a 5 minutes bio break, and we will resume our session with column matching. Okay, so we will start at 8 sharp. I am here. If you are having any question, you can ask. This was the problem basically. This was the problem. We just calculated the pressure drop because of the frictional friction that is present in between the fluid that is flowing through the pipe and the pipe wall. The formula is called as the Darcy-Weisbach equation, that is given here. Fd equals to, frictional pressure drop equals to Fd into L V square, you have 2 GD. V you calculated in terms of volumetric flow rate divided by the surface area, and the rest of the values are given. So FD, I just told in the hint that FD equals to 4F. F is given, so it gives you 0.04, and the rest of the things are known. It is given in the question. Ultimately, you just converted the calculated pressure drop in meters into first in watts, and then from watts to horsepower or brake horsepower, whichever. 1 bhp equals to 746 watt. You used this formula to convert from watt power to brake horsepower, and considering the frequency, that is not frequency, considering the efficiency, just divided it with the efficiency, because whatever the power will be there, it will be having 10% loss, then only it will fulfill the head drop that we are giving and that we are getting because of the frictional pressure drop. Yeah. So hopefully it is you are able to understand that. We'll join after a couple of minutes. Deepti, if you have any question regarding any previous sessions or something, you can ask in the meantime if you want. See, some of the things I am just telling you in the meantime, so you can note down those things. All of the things are not written in the slides. Some things I am just telling while discussing. You can note down those things. If you feel that you didn't know that thing previously, then you can write those things. Okay. So I guess we can restart, resume, and if you are back, I guess. Okay. So now we will move on to our next column matching. So match the following sewage collection system patterns with their characteristic features. So in the left hand column, the collection system patterns are given, sewage collection system patterns. Four different types of sewage collection system patterns are given: perpendicular pattern, interceptor, radial, and zone pattern. And their characteristic features are given in the right hand column. So number one is this pattern is adopted when the sewage is to be disposed of on the land around town. Number two is sewers carrying storm water are laid in such a way so as to seek the shortest possible path to a water course. Number three is sewers are connected to a larger sized sewer that carries sewage to a common point where it is disposed with or without water treatment. And number four is suitable for sloped areas. Now we have to match the left hand column with the right hand column. You can keep this order ABCD as same, and you can tell me the correct order of this RHC. So this correct order you can write in the chat box. I will wait for 1 minute. Just read the question again. Different patterns are there, and if you just imagine those patterns in your mind, then you will be able to understand what should be the their feature. What should their feature be? Yeah. Please write your answer in the chat box. If you are able to match one or two, then also you can write. Let's say B with this, C with that, you can also write in this way. If you are not able to match the entire thing. Otherwise, okay, no issues. I will discuss anyways. So we'll proceed with the solution. So option A matches with 2, option B with 3, option C with 1, D with 4. 2, 3, 1, 4 is the correct answer. So perpendicular pattern is the pattern where sewers carrying storm water are laid in such a way so as to seek the shortest possible path to a water course, because the shortest possible path is a straight line. That's why it is a perpendicular pattern between 2 points. Interceptor pattern where sewers are connected to a large sewer that carries sewage to a common point where it is disposed with or without the water treatment. Okay, so uh, in this type of pattern, the large sized sewer is intercepted by the smaller sewers. That's why it is called as the interceptor pattern. Radial pattern is the pattern which is adopted when the sewage is to be disposed of to the land around the town. So if there is a town and around the town the sewage needs to be disposed of, then the pattern will be radially outward. Simple. Now zone pattern is suitable for sloped areas. It is only left. So it was in the correct order only. The other things you have to imagine. So if you just see the terms perpendicular, intercept, or radial, then the characteristic features are almost obvious. Right. Now we'll move on to our next again column matching. So we have to match the following decentralized sewerage systems with their functionalities. So in the left hand column, decentralized sewerage systems are given. 4 different types of decentralized sewer systems and their functions are given in the right hand column. So the systems are A. Night soil digester, B. Small bore sewerage system, C. Shallow sewerage system, and option D. Twin drainage system. If you have watched Dr. Devapratim's lecture, then it should be obvious to you. Now their functions are provided in the right hand column. Number 1 is one drain carries sewage and other storm water. Number 2, anaerobic digestion of the night soil. Number 3, collects and conveys effluents from septic tanks and aqua privis for offsite treatments and disposals. Number 4 consists of pipe laid at minimum gradients below sidewalk lengths and backyards of planned and unplanned settlements in absence of heavy loads. If you have watched the lectures, previous all the lectures, then you will be able to answer. It is there within the previous 2-3 lectures. Otherwise, I'll wait for 1 minute before answering. Okay, I'll proceed with the answer. So 2341 is the correct order. Night soil digester is the anaerobic digestion of night soil. Small bore sewerage system collects and conveys effluents from septic tanks and aqua privis for off-site treatments and disposals. Shallow sewerage system consists of pipes laid at minimum gradients below sidewalk lengths and backwards for planned and unplanned settlements in absence of heavy loads. And twin drainage system, in case of twin drainage system, one drain carries sewage and another carries storm water. So this term is quite obvious from the name itself. So there must be two drains. One drain will do something else, another drain will do something else. It will be a twin drain system. D goes with one. It was quite obvious. So these three things you have to just tell. Two, three, four. Yeah. And yes, the digestion of nitrile goes with nitrile digester only. It was also quite obvious. So only B and C, just these two options only you have to think it. Yeah, and these two options, A2 and D1, these two options was obvious even if you hadn't gone through these lectures, right? Okay. Now we'll move on to our next MSQ. It is a multiple select question. So more than one option may or may not be correct. So more than one option may be correct or one option also may be correct. So which one of the following statements is or are true concerning sewer designs for the population? Option A, lateral and submain sewers are usually designed for average flows. Option B, lateral sewers are designed for peak flow and submain sewers are designed for average flows of the population. Option C, lateral sewers are designed for average flow and submain sewers are designed for peak flow of the population. Option D, lateral and submain sewers are usually designed for peak flows of the population. So both lateral and submain sewers are designed for average flows. Both are designed for peak flows. One is peak flow, another one is average flow. Which one is correct? That you have to tell. Or more than one option may be correct also because it's an MSQ. Yeah. Again, I'll wait for 1 minute. Okay, I'll tell the answer again. So option D, it is the correct answer. Lateral and submain users are usually designed for peak flow of the population. So both lateral and submain users are usually designed for peak flow. It is basically the design criteria of any water system. Yeah, you have to consider the peak flow only while designing. Because if the, let's say, water demand increases, the flow increases beyond the average range, then you cannot just replace the entire pump. It is not possible for the water supply agency. So the design must be for the peak flow, for the both the lateral and submerged sewers. Okay, you cannot just replace the sewer pipelines if the flow increases. So you have to design keeping the peak flow in mind. And though it seemed a MSQ, yeah, so one option is correct in this case. So now we'll move on to our next MCQ. The work done by a pump in raising water up to a certain height H is defined as option A capacity, option B efficiency, option C horsepower, option D discharge. Please answer. You are not answering. It is not fair. Okay. So horsepower, option C is the correct option. The work done by a pump in raising water up to a certain height H is defined as horsepower. We just discussed this MCQ through a problem where you had to calculate the brake horsepower, right? The what is not there in the option. If what was there in the option, then you had some confusion was there. But what is not there, so only one power unit is there, that is horsepower HP, that you should have answered. Okay, anyways, we will move on to our next MCQ. So when is it necessary to separate sewage flow from storm water flow? Option A, in case of heavy rainfall. Option B, in case of sparse rainfall. Option C, stormwater and sewage flows should never be separated. And option D, stormwater and sewage flow should always be separated. Please type the correct option in the chat box. Okay, we'll proceed with the solution. So, in case of heavy rainfall, separation of sewage flow is required from the stormwater. The reason is quite obvious. So, if the rainfall is very small, the rain doesn't flow profusely or in a very turbulent manner through various places of the land. So that's why it doesn't get much polluted. But if there is heavy rainfall, then the sewage flow is gets highly diluted and the load becomes very heavy to the sewage treatment plant, and also some many other particles comes into the picture. So that's why when the flow rate is very high during heavy rainfall, then the separation of the sewage flow is required from the stormwater. Okay, otherwise it is not much necessary. Now we'll move on to our next MSQ. It is an multiple state question, so more than one option may or may not be correct. Which one or which of the following statements is or are true for upflow anaerobic filter? Option A, suitable for areas where leaching systems are not effective for effective effluent disposal. Option B, can be constructed only as a separate unit and not an extension of the pit toilet. Option C, effluent is introduced from the top. And option D, effluent has high volume of sludge. Please answer in the chat box. Okay, so we'll move on to the solution. First, there is an explanation for this problem. So, secondary treatment of septic tank effluent at lower cost. Suitable for areas where leaching systems are not effective for efficient disposal, like the denser soil and higher water table. Constructed as both separate unit or extension of septic tanks, where effluent is introduced from the bottom, Effluent is clear and free from odor and low volume of sludge. Hence, option A is the correct answer. Upflow anaerobic filters are suitable for areas where leaching systems are not effective for effluent disposal. Okay. Now we will move on to our next MCQ, multiple choice question. In the absence of another actual data on sewage flow, a typical value of gas LPCD is used when designing a conventional sewage system. You have to fill in the blank. So LPCD means liter per capita per day. Option A is 50, option B 100, option C 150, option D 200. In the absence of actual sewage flow data, a typical value of how much LPCD is used while designing a conventional sewage system. When you don't have the actual sewage flow data, what value of LPCD you will consider for designing a sewage system? That is the question. Okay, so we will move on to the solution. 100 is the correct answer. So 100 LPCD of sewage data you have to consider while designing conventional sewage system when you don't have the actual data of volumetric flow rate of sewage. Okay. Now this 100 LPCD you have to multiply it with the entire population. So per head flow, that is the per capita flow, and per day, liters per day LPCD. This thing is given as a thumb rule when the actual data is absent. But the population you cannot be assumed. You have to multiply the entire population of the town in order to uh, design the conventional sewage system for the town. Okay. Now next MCQ is, which one of the following uses a metal tank filled with a concentrated solution of caustic soda or NaOH? Option A cesspool, option B chemical toilet, option C biotank, option B night soil digester. Which one of them use NaOH or caustic soda? A metal tank filled with concentrated NaOH solution. That you have to tell. I'll wait for 1 minute. Okay, so we'll move on to our solution. The answer is chemical toilet. All the other things, chest pool, biotank, night soil digester, don't use caustic soda. Only chemical toilet, where a metal tank filled with a concentrated caustic soda solution is used. Okay, the term itself is obvious. It's chemical toilet. So what chemical is being used? The caustic soda concentrated solution is harmful for biological organisms. Those are used in biotoilet. Okay. Now I'll move on to our next MCQ. The seasonal maximum sewage flow rate is dash times of the average flow rate. To fill in the blank. The seasonal maximum sewage flow rate is how many times of the average flow rate? 1.3 times, 1.5 times, 1.8 times, and 2 times. Okay, we'll move on to the solution. So it is 1.3 times. The maximum average flow rate should be 1.3 times of the maximum flow rate will be 1.3 times of the average flow rate. So F max will be 1.3 into F average in case of sewage. Now, next MSQ, multiple select question. Which of the following statements is or are correct regarding pumping mains and or service reservoirs? Option A, for a fixed discharge, as the diameter of pumping mains increases, the flow velocity also increases and leads to a higher frictional head loss. Option B, as the diameter of the pumping mains increases, the cost increases. Option B, service reservoirs increase the pressure fluctuations within the distribution systems. Option D is, as the discharge increases in pumping mains, the head or lift increases. More than one option may or may not be correct. Okay, so we'll move towards solution. First, there is an explanation. For fixed discharge, bigger diameter pipes are required at low velocity. Diameter reduces implies velocity increases. Definitely, because of the continuity equation, if the diameter reduces, for flowing the same amount of volumetric amount of water, there is less space area available. So the uh, water has to move faster. That means velocity increases, leading to higher frictional head losses. If you remember the Darcy-Weisbach equation, there the head loss was given by the expression H equals to F D into L V square divided by 2D into G. That means there is a V square term. V square means as the velocity increases, the frictional head loss increases proportional to the square of the velocity, right? So it definitely affects to a large extent. Now, if the diameter increases, that implies the cost also increases. Why? Because if there is more head loss, you have to pump. Actually, the pump has to do more work in order to make the flow to happen. Right. So that's why the energy consumption by the pump will be more. Thereby, the cost will increase, and thereby service reservoir reduces the pressure fluctuations. Okay. So option B is the correct option. As the diameter of the pump increases, pumping main increases, the cost increases. It is the correct statement regarding pumping mains and or service reservoirs. Okay. So the decrease of the diameter only leads to higher frictional head loss. The increase in the diameter doesn't lead to uh, uh, increased head loss, frictional head loss. Okay. So now we'll move on to our next, and also the diameter as it increases, flow velocity also decreases. It doesn't increase as per the mass balance or equation of continuity interaction. So if the equation of continuity means the area into velocity remains the constant. That means the volumetric flow rate remains the constant, considering the density of the fluid remains the constant. That means for an incompressible liquid like water, which density doesn't vary much. Okay, so the volumetric flow rate remains the constant. Area into velocity remains the constant. A1 V1 equals to A2 V2 through a pipeline where the water is flowing. It can be assumed. Now next, there is an MSQ multiple choice question. Which one of the following methods is involved in IDF or intensity, duration, frequency curve generation? Option A, Barnard equation. Option B, TAM, time area method. Option C is UHM or unit hydrograph method. And option D is rainfall runoff process simulation. This is how an intensity, duration, frequency curve looks like, IDF curve, where intensity in inches per hour is plotted in the y-axis and the duration of rainfall is in minutes is plotted along the x-axis. So example, 10-minute duration and 5-year frequency is given to you. You have to choose there are different year curves, so you have to choose the 5-year curves and you have to choose the 12 minute duration. So it touches the 5-year curve in this point, and if you just extend in the x direction, so it will cut the y-axis into this point. In this way, intensity became 5 units. Like this way, if intensity and uh, let's say air frequency is given to you, then you can find the duration. And also, if the intensity and duration is given to you, you can find out the frequency, the air frequency. In this way, the IDF curve works. Okay, so if you want to generate this type of curves, which one of the following methods is utilized? That is the question. Barnard equation, TAM, UHM, or rainfall runoff process simulation. I'll wait for 1 minute. Okay, so we'll move towards the solution. The answer is Barnard equation. Barnard equation is used for the generation of IDF or intensity duration frequency curves. Now next there is a problem where you have to calculate the area in meter square required for the dispersion trenches for disposal of septic tank effluent for a population of 100 with volumetric flow rate of sewage Q equals to 130 liters per capita per day or LPCD. Now you have to assume T equals to 4 minutes to calculate the percolation rate. So this percolation rate, you have to utilize this uh, to calculate your desired area of the dispersion trenches. Okay, please try to solve this problem. We have not solved anything till now. Are you able to proceed at least few steps? Why don't you reply, man? Okay. We'll proceed with the solution. So total sewage is nothing but the per capita sewage flow rate into the total population. That means the volumetric flow rate per capita Q into N is the total population, which is nothing but 100. Q is given as 130. It gives you 13,000 liters per day. This is the total sewage flow rate, and it is not per capita; it is the total. And the population, percolation rate. There is a numerical formula which is given something like this: Q into root over T. Q is given in the question as 130 liters per capita per day, and Q is the per capita sewage flow rate, per capita volumetric flow rate of sewage into root under 4. Here it is given in the question T equals to 4 minutes to calculate the percolation rate. So in the numerical formula there is this term T, where you put the T from that problem as it is given equals to 4. It gives you root 4 it means 2. 2 into Q, that means 2 into 130 gives you 260 liter per day per meter square. So liter per day is given to you, liter per day per meter square is given to you. You just divide this with this one, it will give you the solution. So hence the area required is 1300 liters per day divided by 260. Liter per day per liters per day gets cancelled out. And after solving this thing, 1300 divided by 26 gives you 50 meters square. So it is the area required for the dispersion trenches for disposal of the septic tank effluent. Okay. Now we'll move on to our next problem. What is the intensity of the rainfall for a storm of the duration of 10 minutes using the empirical formula in the absence of rainfall records? So you don't have the rainfall records. You have to remember the empirical formula in order to determine the intensity of the rainfall. Only single data is given to you in the question. That is the duration of the storm is 10 minutes. Okay. So yeah. Not solved yet. So we'll solve the problem. The data given are duration of the storm in minutes, it is given as 10. So for this empirical formula, in this empirical formula there are several coefficients. To understand those coefficients, you have to first understand the range of the t. So here you can see the range of the t is falling in between 5 and 20. So it is more than 5 minutes, less than 20 minutes. In this case, the coefficients, those are there in the empirical formula. One of that is A becomes 30 and B becomes 10. So this you have to just remember. Okay. Now rainfall intensity I is given by this formula. 25.4 into A divided by T plus B, where T falls between 5 and 20. So that's why the value of A is 30 and B is 10. By putting these values in this empirical formula, we get the solution, which is the rainfall intensity in millimeter per hour. So this T plus B, that means 10 plus 10 becomes 20. A is 30 and 25.4 is the coefficient constant. After simplification, it gives you 38.1 millimeter per hour. This is the intensity of the rainfall. Okay. Now next MCQ is the total storage capacity of the reservoir is given as balancing storage plus dash storage plus fire storage. So balancing storage is also called as the equalizing or operating storage. Okay. So storage capacity of the reservoir is the sum of the three storages. One is missing. Option A is variable demand. Option B is underground. Option C is breakdown. And option D is runoff storage. So which one of these water storage you can use to fill in the blank here, that you have to determine. Okay, so this is the last question we will be discussing today, as the time is almost up. So we will not discuss any further. We'll again meet at 22nd of September at this time, 7 p.m. Even if not participating, thank you for joining. Only 2 students joined today. So, okay, yeah. Now the solution of this problem will be breakdown storage. So the summation of balancing storage, breakdown storage, and fire storage gives you the total storage capacity of the reservoir. Okay. So we'll end the session here. Hopefully you don't have any questions. Okay, then we'll stop the recording.